All right, so now we're talking about the Dirac equation. I'm just going to get right into this. This is going to be, we want to consider something interesting about the Dirac equation and how it might also look like the Klein-Gordon equation, only when we consider something special here. So we want to consider the Dirac equation. So the Dirac equation, again, is I gamma mu d mu times psi minus m psi. This can be rewritten as I gamma mu d mu minus m times psi. We've done nothing, just bring the psi out. And so this becomes an operator. This is the Dirac operator. We usually denote it like this. So the complex conjugate of the Dirac operator just becomes, write that a little bit better, minus I gamma nu. I'll just labeling these different labels. There's really nothing different here. Minus m. Right. So we can consider now what d star, what this object might look like. Well, this object looks like minus I gamma nu d nu minus m times I gamma mu d mu minus m. Okay, and so we're on our way to something interesting here. Let's just keep on going. So if we do this multiplication out, we get, excuse me, we get d mu gamma mu d nu gamma nu, and because I times I is minus 1, then we have this minus I right here. That's, or that minus sign that's going to give us a positive. Then we're going to get, let's see, plus I m d mu gamma mu minus I m d nu gamma nu plus m squared. And we're going to see that these two guys will cancel because they have the different sign on them, and the nus and the mu's are just, those are just dummy indices. Okay, so now we can rewrite this as d mu gamma mu d nu gamma nu plus m squared. Right. So now let's see what this looks like. This looks like, well, we can rewrite this as 1/2 d mu d nu gamma mu gamma nu plus d mu gamma nu d mu gamma nu and plus m squared. The reason we can do that is because these operators, or this derivative operator, is only going to act on one of these, or one of these matrices, whereas it's in the other case it's going to act on the other. And so this here is essentially, or this is 1/2 of this, and this is 1/2 of this also. And so when we bring them together, it's like saying 1/2 plus 1/2 equals 1. And so then we can consider now, I'm just going to copy paste this. Let's see, copy paste is so nice. So I'm just going to put this right here. I'm going to erase this because I want to add now. Actually, I'll just keep the m squared because I want to add now plus 1/2 d mu d nu gamma nu gamma mu, the same thing, minus d mu d nu gamma nu gamma mu. Here I'm just adding 0 because these two things here are the same thing. So this minus this is 0, right? That's not, so that's, we're really adding nothing in this case, which we can do. But if we notice now, this here forms a commutator with this. And this here forms an anti-commutator with this. Right? So what this ends up being is 1/2 d mu d nu gamma mu gamma nu plus m squared plus 1/2 d mu d nu gamma mu gamma nu. All right, well, this is 0 because, as we've seen previously, the commutator here of our gamma matrices is 0. Right, so what that means is that gamma mu gamma nu minus gamma nu gamma mu equals 0. Okay. So what do we have now? We have equals minus 1/2 d mu, d mu d nu gamma mu gamma nu plus m squared. Okay. We're getting close. We're getting close here because now, if we recall, this here, this is 2 mu nu, because that's what we said that earlier. We said this in an earlier video. And so the 2 is going to cancel with our 1/2, and the eta mu nu, well, that's just a Minkowski metric. We can finally rewrite this as d mu d nu plus m squared. And if we recall, we said that this was this. Well, so what is this? This is the Klein-Gordon equation, right? Because, so we'll say this is K, the K operator, Klein for Klein-Gordon. So what we found is that this object here is equal to this object here. So when we consider the complex conjugate of the Dirac operator, we can recover the Klein-Gordon equation. What is this? So on the surface of this, what does this mean? This means that this operator right here is the Klein-Gordon equation, right? It's a Klein-Gordon operator. What this means is that, again, if we call that the Klein-Gordon operator, its dynamics sort of resembled something that of a wave. And so this here acts as a wave, this thing right here, or this operator, is the operator for a wave equation. All right. So the sun's starting to come in through my blinds here, but that's what this means. This is very interesting. The book goes through this too, and I think this is very interesting, right? So now what I want to do again, as I said before, I previously said that we proposed the solutions in the previous video to the Dirac equation. I'll rewrite the solutions here really quick. So the solutions again, so we said that we proposed that the solutions to the Dirac equation were, we had some label on these things, e to the minus I k mu x mu. And what I said earlier is that I thought I wanted to do this over Patreon, but I'm going to go ahead and just actually do it here. Because now we can see that since there's something of a wave nature in this operator, because it looks something like the Klein-Gordon equation when we consider its complex conjugate. Thinking that this is a solution might be a good idea. So if we had, if that was our solution, we have our Dirac equation, and we're just going to put our solution in here. Minus m mu, like this. Well, what does this give us? When we take this derivative here, we're just going to drop down the k mu, right? And we're going to be able to get rid of that I, right? So we're going to get equals minus I squared k mu gamma mu like this. We're going to get minus m like, I'm just going to write it like this because we're going to have our e to the I k mu x mu minus m e to the minus I k mu x mu, like this. Right, well, we can, if both sides equal 0, then we get that this is k mu gamma mu psi minus m psi. And lo and behold, we have our Dirac equation again, where these things are spinor objects. We just got rid of the time and spatial component of this function, and we can see that when we propose that this is some solution to the Dirac equation, we really just get the Dirac equation back again, with our derivative being replaced by our momentum force vector. Okay. And the book also covers the mass basis for the Dirac equation. And what I'll do here, I'll go ahead and talk about the mass basis in this video. I'm going to do a separate screen here for the mass basis. Again, the mass basis is just something of is something of a convenient notation to use sometimes when we're talking about the Dirac equation. And it's really just a conversion that we do here. And it's a little bit arbitrary when you think about it at first. But I'm just going to briefly touch on this because we're not really going to need it for a while. And if I remember, the book doesn't really go over it that much anyways. And so the mass basis for the Dirac equation is really just, if we have our gamma matrices in this form, or we have our gamma matrices, we can convert them into a mass gamma matrix where we have n like this, right? And so where n equals this matrix, 1, 0, 0, 1, and -1, -1, 0, 0, and 1 and 1. And I'm actually going to have to erase some of this. And there's going to be a 0 right there. Actually spread this out a little bit. There we go. Again, you might think this is an arbitrary matrix, but this is actually very interesting because its inverse, n is equal to 2n. That this is a math thing, right? That this is a math. This is something you can prove it to yourself in mathematics. And again, if this is something you're interested in, I'll put a deeper look at this n matrix in my Patreon page. But again, this is just we're converting between what we've seen so far to something else that we're going to call the gamma matrices in the mass basis. And I won't bear the details on this just because I think it's a little bit far beyond the point. But in the Dirac equation, this would look something like this. Gamma mass, and then we have our mu, and then d mu minus m gamma mass, like this. So now everything is in the mass basis, and yeah, so what this means is that our field again is psi. This is our field, right? So more explicitly, this is our field. This is a field. Again, this was a field, again, when we didn't consider the mass basis. This was a field also when we didn't consider the mass basis. And so we can convert between the two using this n matrix. We convert between the two using this n matrix. Very quickly, we can go over the generalized solutions now to our Dirac equation. The generalized solution looks like this, and it's going to look very similar to that of, our Klein-Gordon equation, where the only difference is now that we are going to want to not just, we're going to want to, here, I'll write it out first. D3k 2 pi 3 2 omega k CR k UR k e to the minus I k mu x mu, and then plus dr k vr k e to the I k mu x mu, like this. So this is our most generalized, again, this is a function of x mu. So if I want to be totally complete here, this here would be x mu. This is our completely generalized form, right? We're saying that this is a wave. We're saying that this is a wave. We have these waves, and the combination of these wave with the minus sign in the I and wave with a positive sign. These here, again, we've seen before already. These are the spin configurations. So we're summing over spin configurations because of this R here. And that's really what's fundamentally different about this and the Klein-Gordon equation. If you, I'm going through the book here really quick to give you what page this shows up on, because this is sort of the punchline. This is the end, if you will, of the Dirac equation, and then after this we're going to get into the Conjugate equation. But in the book, this is on page 214. And yeah, so again, we're integrating over all possible momenta, but we're also summing over all possible spin states. Right, so whereas if we contrast this with our Klein-Gordon equation, again, if I go to the book here, the Klein-Gordon equation, or the most generalized Klein-Gordon equation, I'll rewrite it here, looks like this. We're not summing over any spin configurations because, again, there is no, we're not dealing with spinners. This is going to be d3k times 2 pi 3 2 omega k times ak e to the I k mu x mu plus bk e to the positive I x mu, like this. What is this telling us? This tells us that we have a, I'll call this red, I'll call this one blue. We have two fields, right? We have our spin field, or our spinner field, and we have our our scalar field, these are what they look like. They're integrals. We have, and the interesting thing is that, say at this point, we have an integral at this point, and that's this integral. Similarly, we have an integral at this point also, and we have an integral, but we also have a sum over. Right? So this one here is for our spinner, and this one here is for our scalar. Again, the difference is that in both cases we're summing over momenta, but in the spinner case we're also summing over spin states. And this is the end of chapter, or not the end of, but after this we're going to get into gauge fields. But yeah, so I'm coming up on about 30 minutes here, and so I will, I'll see you guys in the next one. Bye.